Hello, everyone, and welcome to this next talk. Finally, we have reached the point where we can start talking about our solar system, our planetary system. And so, over the coming weeks, we will delve deep into the solar system. And tonight, we'll start with a brief little tour of the solar system. But first, of course, is the quote of the night. Hopefully you recognize this image in the background. It is, of course, the famous pale blue dot image that Carl Sagan waxed poetically about. We succeeded in taking that picture, and if you look at it, you see a dot. Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives on a mote of dust suspended in a sunbeam. Timeless words about this beautiful, beautiful image. Now, the goal here is not just to list off facts about each planet individually. Sometimes that can be useful, but really what we want to do is we want to take on an idea called comparative planetology, and that is where we compare the similarities and differences of each of the worlds in our solar system so that we may ultimately reach some deeper understanding of what our solar system is like, what is going on these planets. This is going to be very different for me. I am very guilty of whenever I talk about the solar system, I just go through a tour and talk about each planet individually without talking about the overarching themes that unite or really differ between each world. So that is what we're going to be doing over the coming weeks. We won't be talking about one day, we're going to be talking about Mercury. The next day, we're going to talk about Venus. No, we're going to talk about groups of planets, comparing them to each other. But before we can compare the planets, we do sort of have to go through a standard tour of the solar system. We have to understand the nature of these individual worlds. If there's any information that you find particularly interesting, and I'm not elaborating on, don't worry, I'm sure we will talk about it when we get to that particular night. But otherwise, we will begin with the most logical place to begin, and that is with the sun. So at the top of each of these coming slides, there'll be some biographical information about the object. I won't specifically read out the numbers for you unless they're important, but they're there for you to look at and learn. So the sun is the largest, the brightest, the most massive object in the solar system. It contains 99.8% of all the total mass of the solar system, making it nearly 1,000 times more massive than everything else in the solar system combined. Although the sun's surface does sort of look solid to us in photographs, it's not actually solid. It's a huge spherical ball of incredibly hot gas, so hot that everything is ionized. So we call it a plasma. And the gas that's been ionized is hydrogen and helium gas. The temperature of the sun is about 6,000 Kelvin or about 10,000 degrees Fahrenheit. The surface looks pretty uniform except for those darker spots that sometimes come across the sun around a cycle of about every 11 years. We have a sunspot cycle of every 11 years. And they only appear dark because they're just slightly cooler than the rest of the material around them. They're not actually that cold. The sun is completely gaseous throughout. It's a plasma all the way down, but the temperature and the pressure increase as we go deeper into the sun. And so that's where the conditions are right enough for nuclear fusion to happen, actually four hydrogen atoms physically coming together, fusing together to form a different atom, helium. And it does this millions of times over. It turns 600 million tons of hydrogen into 596 million tons of helium every single second. That missing 4 million tons is the energy. It's the energy that Einstein says an E equals mc squared. Some of that mass has become energy. And that's the energy that we receive here on Earth, and indeed all the planets receive throughout the solar system. And despite losing 4 million tons of mass each second, the sun hasn't really noticeably changed in the past 5 billion years, and it will continue to keep on doing this for the next 5 billion years. Uh, 4 billion tons is not that big of a mass for something as big as 333,000 Earths. The sun is also the most influential object in the solar system. So its gravity governs the orbits of the planets. Its heat is the primary influence on the temperatures of the planetary surfaces and atmospheres. It's the source of all of the light in the solar system. The planets and the moons all shine because they are reflecting sunlight. In addition, charged particles flowing outwards from the sun make up the solar wind. And when they interact with the planetary atmospheres, in particular our planetary atmosphere, we get the lovely northern and southern auroral lights. And it's all caused by the sun. But nevertheless, we can understand pretty much everything about the solar system without having to involve the sun. So, in the next several weeks, we won't talk about the sun. This is, or if we do, hardly at all. We will delve deeper into the sun in about 6 or 7 weeks. So, uh, this is going to be the first and probably the last time that we'll see the sun for quite a while. The first planet on our tour is, of course, the innermost and smallest planet, Mercury. Mercury is a very desolate, it's crater world with no active volcanoes, no wind, no rain, no life. It has no atmosphere, so certainly there's not going to be any wind or rain or life to breathe that atmosphere. Because it has no atmosphere, you could see the stars in the daytime as long as you're looking away from the sun. You might expect Mercury to be pretty dang hot because of its closest to the sun, but in fact, it's a world of extremes. During the day, it reaches an average surface temperature of about 700 Kelvin, but at night, it's absolutely freezing at only 100 Kelvin. Tidal forces from the sun, we talked about tidal forces a few weeks ago. Because Mercury is so close to the sun, that those tidal forces are much stronger. And so it has forced Mercury into this weird 3-to-2 rotation orbit scenario. So for every 3 rotations on its axis, Mercury has orbited twice around the sun. So it has a 58.6-day rotation period and an 87.9-day orbit, which gives it days and nights that last about 3 Earth months each. Mercury's heavily cratered, as you can see in this image from the Messenger spacecraft, but it does show some evidence of some past volcanism, some plains created by lava flows. There might be some geological activity, and it has a very high density, about 5.43 grams per cubic centimeter. For context, water has a density of 1 gram per cubic centimeter. So that high density indicates that it probably has a very large iron core, and that's sometimes hard to explain. We'll get into some explanations about that possibly next week. The next planet outwards is Venus, typically called the sister planet to the Earth because it's very similar size, only 95% the size of the Earth and 82% the mass of the Earth, and has an atmosphere. But in all other aspects, it is very hellish sister. It's nothing like Earth. First of all, it rotates very, very slowly. It takes about 243 days, Earth days, to complete a rotation on its axis. And that's longer than the time it takes to orbit the sun. So its day is longer than its year. You will be 1 Venusian year old before you are 1 Venusian day old. Furthermore, it also rotates in the opposite direction. It rotates clockwise on its axis. All the other planets in the solar system, except for Uranus, rotate counterclockwise. That's very weird. So something must have happened there to cause that. The surface is hidden by some very dense clouds. And so up until a few decades ago, very little was known about its surface until we got some satellites sent to it, as well as better telescopes here on the ground to use radar to penetrate the clouds and get radar information about the surface. And when we got that information, the surface was very hellish. It had mountains, valleys, craters, lots of evidence of past volcanic activity. And even then, people still thought it was kind of a sister planet to Earth, but now we know it was very different. We know that Venus has a very intense greenhouse effect. Its atmosphere is almost entirely carbon dioxide, which is a greenhouse gas, which means the surface of the planet has been baked. Uh, uh, Heat gets trapped in the planet very effectively. So the surface of the planet is at a temperature of about 470 degrees Celsius, which is hotter than a pizza oven. If you were standing on the surface of Venus and you were able to survive the acid rain, if you held a pizza out in your hand, it would cook in 3 minutes. That's because of the temperature as well as the high pressure. At the surface, the atmospheric pressure is 92 times that of the atmospheric pressure here on the surface of the Earth. So it's a very, very hellish world. But because of that greenhouse effect, it was actually Carl Sagan who realized that Venus has a greenhouse effect. We're putting more carbon dioxide in our atmosphere. Maybe we need to take some lessons from what's happening on Venus and apply it here to Earth. So we still learn some things about Venus, despite it being a very hellish world. The next planet is obviously ours, Earth, the third planet from the sun. It's the only known planet in our solar system to hold oxygen, to breathe, ozone to shield the surface from deadly solar radiation, and tons of liquid water on the surface. In fact, the surface is covered by blue oceans, nearly 3/4 of the surface. Of course, we don't live in the ocean. We live on the rest of the stuff, the continental land masses and a few scattered islands. And at night, of course, those artificial lights reveal that there is an intelligent civilization here on Earth. That's, of course, us. Earth is also the first planet that we've come across in this tour so far to have a moon. The moon is actually pretty dang large compared to Earth. Most moons compared to their planets are pretty dang small. So there's got to be something special happening here to give us such a large moon. We think formed from a giant impact. We'll get into that a lot more next week. And then the last rocky planet is, of course, Mars, the planet we keep sending all the spacecraft to. It's larger than Mercury, but smaller than the Earth. It also has two moons, Phobos and Deimos. You can see two images down there at the bottom right from the Mars Reconnaissance Orbiter, which is still in orbit around Mars. Mars is just chock full of things. It has ancient volcanoes that dwarf Earth's mountains. You can see 3 of them here on the Tharsis Ridge or Bulge. The largest one is just beyond visibility, Olympus Mons. It is so big that if you were to stand on the peak of Olympus Mons and look towards the horizon, the land that you are seeing at the horizon is still part of Olympus Mons. You still haven't reached the surface of Mars. It has a huge canyon, which you can see in this image, called Valles Marineris, Latin for Mariner's Valley, that covers 1/5 of its surface. It is as large as the continental United States. So it kind of makes our Grand Canyon not so grand. Mars also has some polar ice caps made of frozen carbon dioxide, dry ice, and a mixture of some water in there as well. But Mars is certainly not habitable today. There are some dried up riverbeds, which indicates that liquid water might have existed on the surface of Mars in the past, but it's no longer there today. The water probably left Mars probably about 3 billion years ago. It's certainly not habitable today. The air pressure is very low. The temperatures are usually below freezing. The trace amounts of oxygen is not enough to breathe. Most of the atmosphere is carbon dioxide. And there's no ozone. So all of the deadly solar radiation would be hitting you all the time and you die of skin cancer. So terraforming Mars is a lot more work than people make it out to be. It's probably not enough. It's probably too much work to make it worthwhile. But we keep sending spacecraft there. Mars is definitely a world of wonders. There's still some mysteries to Mars that we're trying to figure out. All right, the next planet is much bigger. The biggest planet in the solar system, Jupiter. It's about 11 times the size of the Earth, but 318 times the mass of the Earth. Jupiter is so different than the inner planets, than the rocky planets. We've got to really redefine our mental image of what a planet is. It's so large that its largest storm, which you can clearly see in this Hubble Space Telescope image, the Great Red Spot, it is large enough that 2 Earths could fit inside of it. Our hurricanes here on Earth pale in comparison to the Great Red Spot. Like the sun, Jupiter is made primarily of hydrogen and helium. It doesn't have any solid surface. If you were to plunge straight down into those clouds, first of all, the pressures would kill you first, but you would never reach a solid core to stand on. Jupiter reigns over dozens of moons. As of this presentation, as of the time of this presentation, Jupiter has 79 moons in total. We keep discovering more, so that's why I've got to say at the time of this presentation, we could discover some more in the future. It also has a very thin set of rings, not easily visible from Earth. We didn't really know about it until the Voyager spacecraft visited Jupiter. But 4 of those moons are so large that if they were not orbiting Jupiter and instead were orbiting the sun, we would call them planets. Those 4 large moons are called the Galilean satellites because it was Galileo who discovered them. So those 4, we'll talk about those 4 in more detail later. But just to give you a brief summary, Io is the innermost of the 4. It's the most volcanically active world. Europa may have an ocean of subsurface water. And Ganymede and Callisto might also have subsurface oceans. That's why we really want to go to Europa with a spacecraft, drill a hole in the ice, and go fishing essentially. See if anything comes and pokes at the camera. Although it does beg the question that if we find life on Europa, would that life then be called Europeans? An interesting question. I imagine a whole group of people might have some objections to that one. Moving outwards, we reach Saturn. Saturn is only slightly smaller than Jupiter, so about 9 times the size of the Earth. Slightly less massive, 95 times the mass of the Earth. But it has a very low density. Remember, water's density is 1 gram per cubic centimeter. Saturn has a density of 0.7 grams per cubic centimeter. So if you could find an ocean large enough to put Saturn in, Saturn would float in that ocean. Saturn is made up of similar things to Jupiter, hydrogen and some helium. No solid surface. The most spectacular feature of Saturn is, of course, those beautiful rings. All 4 of the outer planets have rings, but Saturn's are the ones that are the most easily visible. They look solid from a distance. I mean, even that image, it looks like it's like a donut orbiting the gas that is Saturn. But it's actually tons and tons of countless small particles that range in size from dust grains, just float around here in the air on Earth, to the sizes of city blocks. So it's not one big solid structure. It's made up of tinier particles. It also hosts dozens of moons. Recently, it overtook Jupiter in the number of moons. It has 82 total moons so far, 2 of which are geologically active. So Enceladus is sort of Saturn's version of Jupiter's Europa. Except Enceladus is active. It appears to have ice fountains. We've actually caught these geysers with our Cassini probe that used to be orbiting Saturn. So we've actually seen this. We also sort of want to go fishing on Enceladus. And then Titan is the only moon with a thick atmosphere. That's why Titan down there at the bottom right looks so featureless. We're looking at its atmosphere. That's not the surface of Titan. We'll also talk about Titan later on. The next one is Uranus, twice as far from the sun as Saturn is. Much smaller than either Jupiter and Saturn, but still much larger than the Earth, about 4 times the size of the Earth, 14.5 times the mass of the Earth. It is made up of slightly different material than Jupiter and Saturn. It's still got hydrogen and helium, but Uranus has a lot of hydrogen compounds, such as water, ammonia, and methane. And it's the methane that gives Uranus that nice pale blue-green color. Probably the most famous fact about Uranus is that the entire Uranian system is tilted on its side. So instead of orbiting straight up or even at an angle, its angle is pretty much tilted straight down, so straight to the side. So it kind of rolls around the sun as it orbits. We think that this was the result of some sort of huge collision during its formation. But Once again, we're not too sure. We'll have to rely on some simulations for that. But that tilted axis gives Uranus some extreme seasonal variations. If you lived on a platform floating in Uranus's atmosphere near its north pole, you would have continuous daylight for half of each orbit. So you'd be in the daytime for 42 years. And then after a very slow sunset, you'd be in night for 42 years. So very extreme seasonal variations. But despite that, the equator is still the warmest place on Uranus. We're not sure what's going on there, actually. Only one spacecraft had visited Uranus, Voyager 2 in 1986. And much of what we know about Uranus comes from that mission. So write to your Congress people, tell them to tell NASA to send another probe out to Uranus. And similarly, Neptune. Neptune is the furthest planet in the solar system. Slightly smaller, but more massive than Uranus. That's because it has a bigger average density. It's much more strikingly blue. That's why it's my favorite planet. I really love that strikingly blue color. Neptune also has rings and numerous moons, though not as many as Uranus, Jupiter, or Saturn. Its largest moon is Triton. Triton's icy surface has features that appear like geysers, but they spew nitrogen, gas, and ice rather than water. It's also the only large spherical moon that orbits the planet backwards. So most moons orbit their planets counterclockwise. Triton orbits clockwise. And we think that is because Triton was not formed around Neptune originally. It was formed further out in the solar system and was later captured by Neptune. And like Uranus, Neptune has also only been visited by Voyager 2, this time in 1989. So once again, please convince NASA to send some probes out to Neptune. Our tour is not over yet. There's still some objects beyond Neptune. Of course, the dwarf planets, Pluto, Eris, and many others. The information, the biographical information up at the top is for Pluto only. Pluto was known as the ninth planet for about 75 years. But in 2005, some astronomers discovered Eris, conveniently named after the goddess of chaos and discord. And oh boy, did she cause some chaos and discord here on Earth. Because as people, especially my generation, hate that Pluto was quote unquote demoted to a dwarf planet. It's too small to qualify as an official planet, but it's large enough to be round in shape. Personally, I think it's better off as a dwarf planet, because if we're just going by what's round, then we've got to add a bunch of other planets to our list. I think my generation was just upset that we went from my very excellent mother just served us 9 pizzas to my very excellent mother just served us nachos. And I think we like the pizzas better. But, you know, it's a human definition. Humans like to put things into neat, tidy categories, but nature is not as kind. So we're always going to have problems with the definitions we create. They're a man-made construct. But nevertheless, Pluto and Eris belong to thousands of these icy objects beyond Neptune that make up the Kuiper Belt. We'll talk about the Kuiper Belt in just a hot second. These are very far away from the sun. So if you were to stand on Pluto and look towards the sun, it'd just be a slightly larger point of light in the sky. It doesn't really give Pluto much heat. It's pretty much in perpetual darkness. Pluto specifically is also tidally locked with its largest moon, Charon. They're in synchronous rotation. So just like our moon shows the same face to the Earth, Pluto and Charon are tidally locked with each other. So they only show the same face to each other. They also, it's not really a planet-moon system because they orbit a point. Their common center of mass is outside of Pluto's body. So they sort of orbit each other. They're more like a binary system than a true Earth-moon system. A planet-moon system where the gravity is clearly dominated by the planet. It's a very interesting system. And of course, New Horizons really showed us how interesting it was back in 2015. And it's the only satellite to have visited these worlds. And New Horizons is still going as well. We're still learning some information about Pluto and Eris and the rest of the Kuiper Belt objects. So that concludes our brief little tour of the solar system. So I have a question for you. Which of the 4 planets, Mercury, Venus, Earth, and Mars, have had volcanic activity at some point in their histories? A, only Earth, B, Earth and Mars, or C, all of them? So think about your answer, pause the video, and come back. The answer is all of them. Basically, just had a list of what I was saying. They've all had volcanic activity at some point in their histories. All right, so now let's get into some let's look at the broad patterns in the solar system that will hopefully give us clues to how the solar system formed, which is what we'll be talking about next week, by the way. So there are 4 major patterns in the solar system. We've got the patterns of motion among the large bodies, the planets. We've got 2 major types of planets. We've also got smaller things known as asteroids and comets. And of course, there are a couple of exceptions to the rules, which we'll have to explain. So the patterns of motion among the large bodies, there are 4 of them. So the first one is that all of the planetary orbits are nearly circular and lie nearly in the same plane. On the left is a top down, so above the Earth's North Pole, looking down at the solar system. The little inset shows the inner solar system. The larger plot shows the outer solar system. And those positions are accurate to tonight about an hour ago. And you can look at the shapes of the orbits. Even though they're all technically ellipses, they're all pretty dang circular. The only one that you might notice a difference on is perhaps Mercury. Mercury has the most eccentric, remember that term, eccentric orbit of the planets. So that one appears the most elliptical, but all the other ones are pretty dang circular. On the right plot is viewing the solar system edge on. And my line doesn't really do it justice, so maybe I should have made the line slanted, but so that Neptune also falls on that line. But they're all pretty much on the same plane. They're not, jutting out like this. That was another reason why Pluto is a bit different, because Pluto does not orbit on a plane; it orbits up at a tilt. So all the planets orbit pretty much on the same plane. They've got nearly circular orbits. That's one pattern of motion that we'll have to explain. The planets also all orbit the sun in the same direction, counterclockwise as viewed from above the Earth's North Pole. This isn't just a feature of this animation. I didn't just command this animation to do this. This is how they actually all orbit. They all orbit counterclockwise. That's a very key fact that will tell you something about the formation of the solar system. Most planets also rotate in the same direction in which they orbit, with pretty small axial tilts, and the sun also rotates in this direction. So most planets also, just as they orbit counterclockwise around the sun, they also rotate on their own axes counterclockwise. So the 2 exceptions clearly are Venus and Uranus, but all the other ones rotate counterclockwise, have a small little tilt. Mercury has no tilt whatsoever. It's special. And all the other ones are tilted to some degree. So that's another thing we're going to have to explain. And then most of the solar system's large moons exhibit very similar properties in their orbits around the planet. So they all orbit counterclockwise, except for Triton around Neptune there at the right. It'll orbit just clockwise. Here in these plots, the distances of the moons from their planets are to scale, as well as the sizes of the planets, but not the sizes of the moons. Otherwise, we would not be able to see the moon. So the moon, our moon, is pretty far from Earth to make Earth appear that small. Phobos and Deimos around Mars must be pretty close to make Mars appear that big. Here we've got the 4 Galilean moons of Jupiter, a bunch more rounder moons of Saturn, a few round moons of Uranus, and then of course just Triton around Neptune, go in the opposite direction to everyone else. So that's another thing we've got to explain. These are all the consequences of the processes that formed the solar system. The other thing we notice is that there are 2 types of planets. So here's a big table, gives you a lot of information about the planet. So their average distances, their average radii, their masses, their average densities, orbital periods, rotation periods, axial tilts, average temperatures, composition, how many moons they have, and whether or not they have rings. And if you were to stare at this table for long enough, you would notice that we've got two different types of planets. So we've got the terrestrial planets. These planets are close to the sun, all within 2 astronomical units. Very small, all less than 6,500 kilometers in radius, all pretty dang dense. Mars is a minor outlier there. And they're all made of rocks and metals. So we call them the terrestrial planets or the rocky planets. Then we've got another group of planets, the gas giants or the Jovian planets. These are all pretty far from the sun, between 5 and 30 astronomical units away. They're all pretty huge, less than between 72,000 and 24,000 kilometers in size. Not as dense as the rocky planets. So as we mentioned before, Saturn is less dense than water even. And they're made of gases, so hydrogen, helium, and some hydrogen compounds, methane, ammonia, and water, stuff like that. So we got these two different types of planets. That's another key pattern about the solar system that we'll have to explain as well. We've also got tons of these small objects orbiting the sun, the asteroids and the comets. The asteroids are these rocky objects found in the inner solar system. They're usually pretty small, less than 1,000 kilometers across. Up at the top right is an actual, what our eyes would see image of one of them, 243 Ida, taken by the Galileo spacecraft in 1993. Most of the asteroids are located in the asteroid belt between Mars and Jupiter. On the left is a plot of, I didn't make this one, but it's a plot of the positions of many of the known asteroids. So in white and gray are the asteroids in the asteroid belt between Mars and Jupiter. But Jupiter is so gravitationally dominant out there that it's captured some asteroids into its own orbit. So we've got the Greeks, the green asteroids. The Greeks orbit ahead of Jupiter. The Trojans follow Jupiter in its orbit. And on the opposite side, in orange, are the Hildas that are always on the opposite side of Jupiter. So tons of different asteroids, tons of different groupings of asteroids in the solar system. May be convinced by some science fiction movies, some science fiction books, that going through an asteroid belt or an asteroid field is extremely dangerous because the asteroids just constantly colliding with each other. And it's not at all true. Space is really big. Space is mostly filled with space. So the asteroids are not constantly hitting each other. We send spacecraft through the asteroid belt all the time without any issue. So unlike what C-3PO says in The Empire Strikes Back, the odds are not 3,720 to 1. So maybe Han didn't want to know the odds because those were the wrong odds. That's my one little Star Wars complaint. Further out, we don't see as many asteroids. Instead, we see comets. These are not rocky objects, but icy objects, and they're primarily found in the outer solar system, although they do come into the inner solar system every now and then. Comets are pretty small. They're no bigger than 16 kilometers or 10 miles across. The top right is an actual image of the comet 9P Temple from the Deep Impact mission in 2005. And there are two spots where comets come from. So we've got the donut-shaped region just beyond Neptune called the Kuiper Belt. So think of that like an asteroid belt, but instead of between Mars and Jupiter, it's just beyond Neptune. That's where Pluto and Eris are, as well as 100,000 other objects, Kuiper Belt objects. And then we've also got the hypothetical Oort cloud, which is a much more distant spherical swarm of trillions of comets. Out there, it's so dark, the comets aren't really reflecting much light. So it's not like we can point a telescope and say, hey, that object is in the Oort cloud. But it's one of those things that we're going to say this is how things work. We don't have any concrete evidence to back it up, but it works better if we say this is how it works. So for all intents and purposes, the Oort cloud is a thing, although maybe it's not. So that's asteroids and comets. And the last thing, here's a question. I'm getting ahead of myself again. Which of the following three kinds of objects resides closest to the sun on average? So A, comets, B, asteroids, or C, Jovian planets. So think about your answer and come back. All right, the correct answer is B, asteroids. Remember, asteroids are in between Mars and Jupiter, so they're closer than all the other Jovian planets. And comets, I just said, pretty much stay on average outside of Neptune. So B is definitely the correct answer. And we've got some exceptions to the rules. You've seen some of those exceptions already as I walk you through the other three rules. So most of the planets rotate in the same direction they orbit, but Venus and Uranus are the exception. So Venus spins backwards and Uranus spins on its side. We've got to explain that. While most planets fall into those two categories, terrestrial or gas giant, the dwarf planets like Pluto don't clearly fall into either of those categories. And then, as I mentioned before, planetary moons are usually much smaller than their planet, except for the Earth-Moon system. So even if a theory explains those big picture patterns that we see, there needs to be room in it to explain the exceptions as well. And we'll get into that theory next week when we talk about the formation of the solar system. But before we talk about the formation of the solar system, before we end tonight, we need to understand how we learn information about the solar system. And much of our knowledge comes from telescopic observations, typically using the Hubble Space Telescope or some ground-based telescopes. But we have learned a lot by sending robotic spacecraft to the planets in the solar system. And robotic spacecraft tend to come in three flavors. We've got flybys, orbiters, landers and probes, and sample return missions. So flybys are generally cheaper than other missions because they're less expensive to launch into space. Launch costs tend to depend mainly on the weight of the spacecraft, and sending a spacecraft out into the solar system with its own fuel takes up a lot of weight. And then once flybys are useful because once they're outside of the Earth's atmosphere, there's no friction or air drag in space. So that means the spacecraft can keep going without having to spend any fuel. Moreover, flybys can often visit multiple planets. So, for example, Voyager 2 visited all 4 of the outer planets in the solar system. It launched from Earth in 1977. Reached Jupiter 2 years later, Saturn 2 years after that, Uranus 5 years after that, and Neptune 3 years after that. So it took over a decade for Voyager 2 to go from Earth to Neptune. And Voyager 2 and its sister Voyager 1 are still going. We're still talking to them. They're well outside the solar system now, but we're still talking to them and getting information back from them. You can see in that GIF up at the top right, that Voyager is able to do this because it flew close enough to each of these planets to rob some gravitational, some orbital energy from those planets, essentially causing it to slingshot onward toward the next planet. This is called a gravitational slingshot, and it can save costs on fuel. And although a flyby only offers you a very short window of study, it can give you some really valuable information. So flybys generally carry small telescopes, cameras, spectrographs, and because they're all those instruments are brought relatively close to these worlds, they can get very high resolution images and spectra than even the largest telescopes in orbit around the Earth. In addition, they get information that would be very hard to get from Earth. So, for example, Voyager 2, as I mentioned briefly before, helped us discover Jupiter's rings and learn about the rings of Saturn, Uranus, and Neptune. They also might carry instruments that allow you to measure the local magnetic field strength or to sample interplanetary dust. The gravitational effect of planets on their moons and their moons on the spacecraft also tell you information about the object's masses and densities. All that information can't really be gained from Earth. can really only be gained by sending something out there and having it interact with the planet. So they're very important. Uh, if we don't care about how much fuel we need to send, then we can do things about orbiters. So orbiters are able to stay around the planet for a much longer amount of time because they carry their own fuel with them. So they can change their own trajectory to insert themselves into orbit around the planet. And they still carry the same instruments that flybys carry: cameras, spectrographs, telescopes, instruments for measuring magnetic field strengths, radar. One particular probe, which I'm highlighting here, is Magellan, which launched in 1989. And it went on to go give us radar images of Venus. So here you can see two radar images that it took: the Dickinson crater and the pancake mounds in the Liban-Farah region. Pancake mounds are essentially really flat volcanoes. We'll talk about those in about 2 weeks. So those are all very, orbiters are very important as well. Going one more step, we can actually land our spacecraft on some object. So Mars has probably the most landers and probes than any other object in the solar system. But most people know about the Martian ones. I wanted to talk about this one. Huygens is a lander that was attached to the orbiter Cassini. And in 2005, Huygens detached itself from Cassini and flew into Titan, Saturn's moon with the atmosphere. On the left, you can see the landing spot of Huygens in the region known as Shangri-La. That is a radar image from Cassini of the surface of Titan. And there in the center, you can see an actual image that Huygens took of the surface of Titan. You see there's tons of rocks. There's some flatter parts in the midground. There's maybe some more flat parts in the background. It's pretty true color as well, I believe. Huygens lasted for about 90 minutes before we lost contact with it. But it's very cool. We put a probe on Titan. It's very awesome. And the next, the final type are sample return missions. These are more of a recent invention. The benefit for sample return missions is because probes and landers, they do carry out good experiments, but those experiments and the instruments that allow those experiments to happen have to be designed in advance, and they have to fit on the spacecraft. And a planet can throw a surprise at us that if we don't have the right instruments to really get the data that we want, we're just out of luck there. Sample return missions break that. They allow us to learn more information by briefly touching down on an object, coming back up, and sending that sample to Earth. So one great example of this is the Hayabusa 2 satellite from the Japanese Space Agency. And it went and investigated the asteroid in the top right corner, 162173 Ryugu. And you can actually see this GIF of Hayabusa 2 touching down on Ryugu in 2019. It collected a sample, and I believe that sample's already made its way back to Earth for us to analyze. This is very, very cool. NASA also has its own sample return mission from an asteroid as well. So we've got 4 different types of missions. Many missions combine objectives. So, for example, the Galileo mission to Jupiter included an orbiter that studied Jupiter and its moons, as well as a probe that entered Jupiter's atmosphere. Cassini was an orbiter around Saturn, but it also had the Huygens probe that landed on Titan. This is a table of all the currently active spacecraft in the solar system, 27 of them. Primarily from NASA. The Americans are the ones who are doing most of the work, but there are some Chinese spacecraft, a few Japanese ones, and some from the European Space Agency, the ESA. Most of them are on Mars. A plurality of them are on Mars, 12 of the 27. And the next most are around our moon because it's the easiest thing to get to. and then everyone else kind of shares some objects. So we got 5 around the moon. Um, uh, 1 is en route to Mercury. That is the satellite Bepi Colombo should make it there in about December of 2015. That's a European and Japanese spacecraft. We've got a Japanese spacecraft around Venus called Akatsuki. 12 around Mars. The oldest one is from 2001, the 2001 Mars Odyssey. We've got a tie for the 4 newest. We've got the Emirates Mars mission, the first Arabic satellite from the United Arab Emirates, landed there in February of this year. Tianwen-1, also in February this year. It's an orbiter and a rover from the Chinese Space Agency. And then Perseverance and Ingenuity, a rover and a helicopter from NASA. The Emirates Mars mission I didn't mention is an orbiter as well. There's 2 around asteroids. Hayabusa 2 has done its mission at Ryugu and is moving on to some other asteroids. NASA's version is OSIRIS-REx. It is investigating the asteroid Bennu, and I think it's on its way back. The sun currently has 1 in orbit around it. The other one, the solar orbiter, is en route to reach its destined orbit by 2023. Jupiter has 1 currently, Juno. All the rest of the outer solar system planets, Saturn, Uranus, and Neptune, don't have any at the moment. We've got New Horizons in the Kuiper Belt, and then beyond the solar system, we've got the 2 Voyagers, Voyager 1 and 2, the oldest currently active spacecraft in the solar system, working since 1979. So that concludes sort of the overview of the solar system. Next week, we will talk about the formation of the solar system, trying to explain all those patterns of motion that we just talked about. So with that, I will end tonight's talk. Let me know in the comments or direct message me what you think about so far if you have any questions. Otherwise, I will see you next week.